Alrighty, so we are just going to continue on with the feedback circuit work that we're doing. So previously we did all our component calculations for the poles and zeros part of the circuit. So let's just take a look at the circuit and I'll show you visually where we are. So we just finished doing the R comp Z, C comp Z, R comp P, and C comp P. And I explained what those do in that last video, so go check that out if you have any questions regarding that. So now we're going to work on the rest of the circuit. So that's going to be covering the resistors such as RFBU, RFBB, RLED, RTL bias. We're going to talk about the optocoupler, and then we're going to talk about this shunt regulator a little bit as well. So let's just jump right into it. So the shunt regulator and optocoupler work to send the feedback signal back to the flyback controller. So I kind of talked about that in the last video. So that's like the entire like mechanism of action for this part of the circuit, is that we're taking a signal that is on the output of our converter, and then we're sending it back to the little computer to we're basically sending data back to the controller so that it can adjust accordingly, right? And so we're all of the components are just working to send a reliable, stable, and integral signal back to our controller, right? So it's pretty simple. So like I said, the main components that we're going to be focusing on are going to be the shunt regulator, which is going to be U3 on our schematic, and I'll show a detailed overview of our schematic in like some later videos. We've got the optocoupler, which is U2. We've got RLED, RTL bias, RFBU, and RFBB. So quick note on the shunt regulator. So I feel like I need to cover how shunt regulators work in a separate video. Because I think it needs its own standalone video. So I'll say it's kind of outside the scope of this example project. So we're just gonna show how we're using one in this case, right? So the data sheet actually does us a nice favor, and it shows the exact one that they use. And so we're just going to use the same one that they use in their example, right? Because, you know, if it's not broke, don't fix it. So we're going to be using this one right here by TI. And that's pretty much all you got to worry about for the shunt regulator. Nothing much more to be said there. So the next thing we're going to work on is the feedback resistors, right? So just quickly looking at this circuit, what we're doing is creating a voltage divider that then goes into the input of our shunt regulator. So our shunt regulator has 3 pins, and without getting into too much detail about how it works, this is basically just setting a threshold level for our shunt regulator right here. So we're taking in our case it'll be 24 volts, and we're dividing it down and inputting it into our shunt regulator. So that's pretty much what we're doing, and they give you a nice equation in our data sheet. I don't know, I mean, I wrote it down and it was up there actually. Yeah, so we're on this section of the data sheet. So I mean, we'll just show how I input those in there. So RFBU equals V out minus the ref of TL431, which is our shunt regulator. So this is the reference voltage of our shunt regulator divided by the current saturation threshold of our shunt regulator. So basically, like I said, it's a reference voltage of our shunt regulator. So if you look on the data sheet of the shunt regulator, it's listed as 2.495 volts. Then the reference input current, they chose 1 milliamp, and that's just to properly saturate and give like a steady constant signal into our shunt regulator. So that's kind of how that comes out. And then we know V out already is what we specified to be 24 volts. So hopefully these are all, you know, pretty simple. You just plug it in, do the calculations. We get 21,505 ohms for our resistance value for our FBU, and then for our FBB, we have the same. We have another equation, right? So it's just RFBU times this quantity again. We just covered what REF-TL431 is. So plug in the numbers again. We get 2,495 ohms on RFBB. Okay, so that's pretty much all you need to know about that. Again, just make sure your resistors are sized appropriately in terms of their power dissipation rating so that they can handle the 24 volts across them. So that shouldn't be too big of a deal. And then also for package size. So again, this signal, like looking at this part of the circuit, there's going to be like where things are really dense are right around this chip right here. Other than that, we have all the room in the world because we have these, like this transformer is going to be huge, and so are the input caps, and output capacitor is going to be pretty big. So as terms of like what's responsible for most of the board size, we're looking at stuff like this. So you can easily fit in an 0603 anywhere you need to. So 0603 is a fine package size to go for this. Let's see. Okay, so the next thing in my notes is going to be covering the optocoupler. So again, I think I'll make a separate video on how optocouplers work. I don't think they're too complicated. But I still want to cover like some mechanisms of action and explain in detail like why we need an optocoupler and stuff like that. Yeah, and there's also a reason why we don't really need to cover it too much right now is because the datasheet just gives us the optocoupler as well. So they use this one right here by onsemi. So just choose the same one they did and then wire it up the same, and it's going to work. It's not, it's pretty simple. So moving on, so this is when we actually have a nice feat of engineering, and I'll show you this one trick that engineers hate. Okay, so we'll start. So when you get to the datasheet part where it's talking about RLED, so that's where we got to scroll down a little bit. So actually, when you start getting this part of the datasheet, you're probably starting to get a little bit nervous because you're like, okay, what's up with these SF, these functions? I'm used to actual, I'm comfortable with some algebra, right? Maybe even a little bit of calculus or something, right? But then we're throwing in these, like, since when is my component value, I have to follow an actual function, right? If it keeps going down more and more, it doesn't get any better. It just keeps going, and then, okay, that one looks pretty normal. But then they hit you with the only equation related to RLED is this one and this one, and this sets it equal to a function. So you're like, okay, this is not an actual value. Like, what on earth am I supposed to do? And then they give you this horrible thing that just says RLED needs to be less than this whole quantity. So I'll cover some notes on how exactly I went about doing this, and share with you my super secret trick. So just quickly covering what the datasheet says is, and I'll show you where it says it. So let's see. Okay, so it says the required value for RLED can be selected to achieve the desired crossover frequency by setting the total loop gain equal to 1. So I think, okay, so G total is the total loop gain, right? So they're saying they're setting this equation equal to 1. So that's how we get this part right here, right? And then if you look in right here, in this part of the equation, they have G opto of S, right? And that's that equation up there. So what you want to do is substitute this quantity right here for G opto of S. And what that looks like is this, right? So hopefully you can kind of see where this is going, and that these are all multiplied together, right? Which is pretty nice, because what that means is you can just multiply across the RLED value that's in the denominator of one of those quantities, right? So looking for, so this, whenever we plug this in, kind of like I said, so this is what it looks like on like step 1, right? Where we have substituted 1 for G opto, or G total of S, and then we have plugged in this value for G opto of S, right? So RLED is in the denominator. So what I'm saying is, since these are all multiplied together, you can just multiply this across, and that's how you get RLED. And then as far as the less than or equal to thing, I think that this has something to do with feedback systems, in terms of creating a stable feedback response. And I'll go in more depth about this, why they did this, in a later video when I talk about feedback systems. So don't worry about too much anyways, because my ultimate conclusion with this is this equation is pretty useless to me. Like, what I want to say is it's really complicated. Like, we have to deal with like functions, and this just looks like it's going to be a headache and a whole lot of math when we're just looking at it, right? And then, I mean, looking at this too, like, what on earth am I supposed to do? So what I did was this one trick, which is, if you don't like an equation in a datasheet, then use a different one. And you're probably like, okay, what WTF does that mean? And the answer is, here, let me scroll down here. Okay, so this is the application note for a different power supply that has feedback, like has a feedback system in it as well, right? And what I want you to notice is look at the similarities, right? This is the spitting image of our circuit, right? Look at this. Okay, we got our feedback resistor divider right here. We got our poles. We got our zeros, or actually I don't know if they're shown on this one, but this is exactly the same as this, right? Even this part, right? We have R bias and RD, they're the same, right? So what it follows that there's some equations in this data sheet right here and this little application note, then they're probably applicable to our project as well. So sure enough, let's just use this other sheet for simplicity, so we can easily toggle between the two. You just gotta scroll all the way down. This is like section 12 of this data sheet. And pause the video if you want to check out what application note. You can look it up yourself. Let's see, where is it? What section? We're looking for section 12, step 8. Step 12 right here. Okay. So if you scroll down some more and a little bit more, then you see they actually give you some equations for, here we go, right? So what I want you to look at is, okay, so see this, we have RD and R bias. Well, what are the equivalent variables for us? So in this data sheet, RLED looks like it's equivalent to RD, and then R bias looks like it's equivalent to RTL bias, right? So basically what we need to do is whatever equation they use to solve for RD, that's what we're going to use to solve for RLED. Right? It's brilliant. I know. I'm amazing. Just drop a like if you appreciate that, okay? Also subscribe. That really helps me out. Helps me come up with some of these amazing tips and tricks for you guys. Right? So it's pretty simple now. That means this equation has RD in it and this one has R bias in it. So look at, okay, I want you to look at this thing, right? We got 3 variables in there versus this monstrosity of an equation right here. It's like, no, I ain't touching that. No way, Jose. No, that's not happening. Okay, so we're going to use this one. It's way simpler and it's going to work. And we even kind of, and I'll show you how we can kind of compare to make sure our answer actually comes out to make sense. So if you just read this data sheet, read this section, and I'll explain to you where we kind of change. We also have to actually use some critical thinking skills to make sure it matches perfectly. So let's just scroll down to the part where I plug in my equations. So the data sheet, basically what I've done is I've quote unquote translated the equation that we just looked at to the one that's applicable for us. So we have V out, which is our output voltage that we specified. VOP is the optodiode forward voltage drop. So what I did is I went into the data sheet for the optocoupler that we are using, and it says that the optodiode forward voltage drop is 1.2 volts. So instead of whatever they use in their equation, I think they said it's typically 1 volt or something like that. Yeah, it says VOP is, which is typically 1 volt. We're not using 1 volt. We're using 1.2 volts. And then 2.5 is just a constant. So we're putting 2.5 in there. And then it needs to be greater than I feedback, which is the feedback current of, and I don't know why I didn't finish that note. But I think they end up putting it, let's see what we set I feedback needs to be greater than, it needs to be greater than 1 milliamp. So we set it equal to 10 milliamps here, so we can look at the data sheet. So there, I feedback is the feedback current of the FPS, which is typically 1 milliamp, for example. So we end up using 10 milliamps just for headroom, right? Because it says it needs to be greater than 1 milliamp. So 10 is more than enough. And in this case, FPS is their controller. So 10 milliamps would be fine for our controller. It can handle it. So then you just plug all these in and you solve for it, and boom, you get RLED equals 2.03 kilo ohms, right? Look at that. We did it. We hacked the system and we got an answer, and you know, we're gonna stick it in there and it's probably gonna work. So that's what testing is for, right? Okay, if it doesn't work, then you go back and you kind of figure out what were we going wrong. But no use in putting all this effort into having to solve these complex equations when this is gonna work, right? Okay. So moving on to the next equation, now we're going to calculate our value for RTL bias. So what they are saying is VOP divided by RTL bias needs to be greater than 1 milliamp. So we know VOP, we've already established that to be 1.2 volts. And then, so to calculate RTL bias, what I quickly want to do is go over to our original data sheet where they mention, I think they mention it's early on where they talk about RLED, because they mentioned that they set, let's see, okay, right here. They said our opto has already been set to 1 kilo ohms, but the value of RLED has not yet been. So this is again something that it's kind of confusing. Is our opto in this case is our RTL bias. So I don't know why they changed the name of that. So, but yeah, that was something that's a little bit confusing. Anyways, so they said to 1 kilo ohm. So look what happens if we plug in 1 kilo ohm, we get like 1.2 milliamps, right? So these values, what I'm saying is they converge on like, according to both equations, 1 kilo ohm is valid, right? So it just shows, this is like reinforcing the idea that our strategy worked of using different equations. So that's kind of how I ended up, that's how I got these values right here. That's what I used. So I don't really have too much more to say other than, like, again, we're going to keep rehashing this, make sure they're appropriately rated for their power ratings. Again, 0603 will be fine for this. You can even go bigger. You got all the space in the world on this side of the board, so don't worry about it too much. So yeah, that's pretty much all I got to cover for the. So this completes the entire feedback portion of that, right? So now after you've made it through this video, you've finished pretty much all of the right side of this circuit right here. So we're actually closing and we're almost done. We only have a few more. We got 2 more sections I want to cover for the actual circuit design. And then we'll proceed on and I'll cover, we're just going on with the rest of the series. So yeah, thank you so much if you made it to the end of the video. Like I said, drop a like if this helped you out. It really helps my channel out a lot, so I'd really appreciate that. Subscribe if you want to stay up to date with the rest of the videos that I'm posting in this series. So I'm just going to be posting them one after the other for the next like few months or so. Also, if you're interested in any other electrical engineering related content, then I also post a lot of other stuff like that, like Altium tutorials, and like I'll give detailed explanations of how things work. Like I'm going to be covering the shunt regulator and the optocoupler and stuff like that. So if any of that stuff interests you, subscribing is probably going to be an easy way for you to stay up to date on all that stuff. And so yeah, thank you so much, and hopefully I'll see you in the next one.